The moment you blinked, right now, and I mean this very instant, you are looking at something. Maybe it's a screen, maybe it's a book, maybe you're sitting by a window and there's a tree outside and a bird just landed on a branch and you thought, there it is, right now. But here's what I want you to sit with for just a moment before we go any further. That bird you saw, you didn't see it now, you saw it in the past. I know. You're thinking, Feynman, come on. It's sitting right there on the branch. That's not the past. That's the present. That's now. But I promise you, by the time we're done here, now is going to feel a lot more slippery than you thought. And the wonderful thing, the thing that keeps me up at night in the best possible way, is that it isn't just philosophy. It isn't just a word game. The physics of it, the actual equations, the experiments, all of it says the present moment is not as universal as it feels. Now let's find out why. Let me start with what seems like a very simple, very obvious idea. When you and I say now, we mean the same instant. We mean the shared moment. You snap your fingers, I hear it. That's now, simultaneous, together, the same slice of time. This idea is so deeply baked into how we think about the world that it almost doesn't feel like an assumption. It feels like a fact, like gravity, like 2 + 2. But assumptions are funny things. I've spent most of my life being suspicious of assumptions, especially the comfortable ones, the ones that nobody thinks to question because they're so obvious. Because in my experience, that's exactly where nature hides the most interesting surprises. Here's a simple version. Imagine two friends, let's say Betty and Petty, standing about 30 feet apart from each other in a field. Now, exactly in the middle between them, I set off a little firecracker, a pop of light and sound. Both of them see the flash at the same time because they're the same distance away. Both of them hear the bang at the same time for the same reason. They'd both agree that firecracker went off now, at the same moment, for both of us. Good, comfortable. Now let me make it a little more interesting. What if instead of standing still, Petty is on a train moving toward that firecracker, and Betty is standing on the platform at rest? When the firecracker goes off, the light from it travels toward both of them, but Petty is moving toward the source, and Betty is standing still. From Betty's point of view, the light reaches both of them at the same time. But from Petty's point of view on the moving train, she moves toward the light, so she'd swear up and down that it reached her first. Who is right? Both of them. That's the whole trick. And that trick has a name, the relativity of simultaneity. But wait, I'm getting ahead of myself. Before we get to Einstein, let me tell you about light, because light is the reason any of this matters. The speed of light, about 186,000 miles per second. That is, by every measurement we've ever made, the fastest that information, any signal, any influence, can travel through space. Nothing beats it. Nothing even ties. Now, the reason this is so startling, and it really is startling even to me, even after thinking about it my whole life, is that it means everything you perceive is delayed. When you look up at the night sky and you see a star, you are not seeing that star as it is right now. You are seeing it as it was when the light left it, which could be years, decades, centuries, or even millions of years ago. Some of those stars might not even exist anymore. They could have exploded, collapsed, gone dark. And we'd have no idea because the light hasn't reached us yet. Now you might say, Feynman, sure, but that's stars. That's far away. What about here on Earth? What about normal everyday things? Well, the same principle applies. It's just that the delays are much, much tinier. The sun is about 93 million miles away. The light from it takes about 8 minutes to reach us. So when you look at the sun, and please don't look directly at the sun, you're seeing it as it was 8 minutes ago. That's not now by any meaningful definition. And your friend across the room? Light takes a tiny fraction of a nanosecond to cross the room. Practically nothing, but it's still not zero. There's still a delay, even the signals in your own nervous system. The electrical impulses that travel from your eye to your brain, those take somewhere around 1/10 of a second. The now you experience is already a tiny bit in the past by the time you experience it. I find this genuinely wonderful. The brain is constantly stitching together these slightly delayed signals from your eyes, from your ears, from your skin, and weaving them into a seamless story called the present moment. But it's a constructed story. It's an edited film, not live television. But this is just the beginning. The really wild stuff comes when you start asking what happens when someone is moving. Because that's where Einstein comes in. And Einstein, as usual, makes things gloriously complicated. In 1905, Einstein published his special theory of relativity. And at the heart of it, the engine that drives all the strange conclusions, is one simple postulate. The speed of light is the same for all observers, regardless of how fast they're moving. That's it. That's the premise. It sounds innocent. It sounds almost boring. But the consequences are not boring. The consequences are magnificent and disorienting. And they include, among other things, the fact that two events that are simultaneous in one reference frame are not simultaneous in another. Let me give you Einstein's own version of this, which I love. Imagine a very long train moving at high speed. Two lightning bolts strike the ground simultaneously, one at the front of the train, one at the back. An observer standing on the embankment, exactly in the middle between where the bolts struck, sees both flashes at the same time. He says, "Those bolts struck simultaneously." Now there's a passenger on the train, sitting in the exact middle of the train, equidistant from both ends. She's moving toward the front of the train, where one bolt struck. Because she's moving toward the front, she moves into the light from the front bolt before the light from the back bolt reaches her. She sees the front flash first. She doesn't make a mistake. She doesn't have bad instruments. She correctly concludes that the two bolts did not strike simultaneously. The front bolt struck first. Both observers are right. Both are using correct physics, and they disagree about whether two events happened at the same time. Now, let me be very careful here, because this is a place where people often get confused. This is not about seeing. It's not about the delay of the light reaching your eyes. Einstein already corrected for that. The observers in this experiment are accounting for the travel time of light. Even after the correction, they still disagree. His means that simultaneity, the idea that two events happen at the same time, is not an absolute fact about the universe. It's a relative fact. It depends on your state of motion. Two events can be simultaneous in one frame of reference and not simultaneous in another. And neither frame is more correct than the other. Here's a picture I like. Think of space and time together as a loaf of bread. The slices of bread represent nows, all the events happening simultaneously. When you're at rest, you cut the bread straight across, horizontally. Those flat slices are your no's. But when you're moving, you tilt the knife. You cut the bread at an angle. Your slices are different from mine. We're cutting the same loaf, the same universe, but we carve it up into different nows. Neither cut is wrong. They're just different. This leads us to something called the space-time interval. Instead of thinking of space and time separately, 3 dimensions of space, 1 dimension of time, Einstein showed us they're woven together into a single 4-dimensional fabric. Space-time. And the thing that is absolute, the thing every observer agrees on regardless of their motion, is not the time between events, or the distance between events. It's a combination of both. The space-time interval, your slice through space-time, depends on how you're moving through it. Someone moving relative to you has a different now, not because of some illusion or trick of perception, because of the actual geometry of space-time itself. I remember the first time this really landed for me, not just as algebra on a page, but as a real statement about nature. I had to sit with it. Because it means that when I say, right now, my friend in Japan is having dinner, that statement has no absolute meaning. In my rest frame, in my slice of space-time, yes, there's an event I'd call simultaneous with this moment. But someone moving fast enough relative to me would have a completely different slice, and in their now, my friend in Japan might be doing something entirely different. The question, what is happening right now, elsewhere in the universe, doesn't have a single answer. Now, here's where I want to push even further. Because what I just described is special relativity, and it's strange enough. But when you add gravity to the mix, when you go from special relativity to general relativity, the situation gets even richer. Time itself slows down near massive objects. Clocks tick slower at the bottom of a gravitational well than at the top. This isn't metaphor. It's been measured. Precisely. We've put atomic clocks on airplanes and compared them to clocks on the ground, and the airborne clocks run slightly fast, because they're slightly farther from Earth's gravity. So not only does your state of motion affect your position in a gravitational field does too. Up here on the surface of the Earth, time ticks at a slightly different rate than it would deep inside the Earth, or high above it. The venows we share aren't quite as shared as we think. All right, so we've established that simultaneity is relative. Your now depends on your motion. Different observers slice up space-time differently. This naturally raises a very deep question. If there's no universal now, what is time exactly? Is it something that flows, or is it more like space, something you can move through in principle? This is where physicists and philosophers start talking about what they call the block universe. Let me explain what that means and why the physics seems to point toward it. In our everyday experience, we feel very strongly that the past is fixed. It's done. It's over. It's recorded in memory and in rocks and in old photographs. The future is open. It hasn't happened yet. It's undetermined. And the present is this razor. Thin moving edge between them. The now is special. It's the only moment that's real. But here's the problem. The equations of physics, including Einstein's equations, don't work that way. The equations don't say, this is now, this is past, this is future. They describe a four-dimensional space-time where all events, past, present, and future, simply exist. All the events that have ever happened, are happening, or will happen, are laid out in this four-dimensional structure. There's no flowing, no becoming, no special, now that marches forward through time. Think of a movie reel. All the frames are there at once, stacked up in the canister. When you thread the film through the projector, you get the illusion of motion, of events unfolding in sequence. But the frames don't actually move or flow. Frame 17 doesn't become frame 18. They're all just sitting there, in order. Static the movie is a story we construct by running through them. The block universe is a bit like that, all the moment. The feeling of now is the projector lamp. It illuminates one frame, but the other frames aren't gone or non-existent. They're just not currently lit. Now, I have to be honest with you, and I always try to be honest about what we know and what we're still figuring out. The block universe isn't a proven fact, the way E equal mc squared is a proven fact. It's an interpretation of the physics. It's what the equations seem to be saying. But equations don't come with a translation guide for what they mean about reality. What I can say with confidence is this. The physics tells us very clearly that there is no preferred now in the universe, no cosmic clock that everyone agrees on, no master timestamp that says this is the current moment, the sense of now being special, being real in a way the past and future are not. That sense comes from us, from our biology, our memory, our consciousness. It's something we impose on the universe, not something we read off from it. Here's a beautiful one that I think really drives this home. It was pointed out by the physicist Roger Penrose. The Andromeda galaxy is about 2 million light-years away from us. Now consider two people on Earth, one walking toward Andromeda, one walking away from it. Because of the relativity of simultaneity, their nows, the slices of space-time they call simultaneous with this present moment, are tilted differently relative to Andromeda. Even though they're walking slowly, just a few miles per hour, the tilt is enough that when projected out 2 million light-years, their nows in the Andromeda galaxy differ by potentially thousands of years. One of them might have now in Andromeda coinciding with a time when a certain alien civilization is deciding whether to launch a fleet of spaceships. The other person's now in Andromeda might coincide with a time when that decision is already history. Neither of them can influence events in Andromeda right now. The information can't get there fast enough. But still, the idea that two people walking slowly past each other on a sidewalk have different nows 2 million light-years away is deeply, genuinely strange. I want to be careful here to not overstate this. The fact that simultaneity is relative doesn't mean time is meaningless or that we can't say anything about it. Within a given reference, cause and effect still hold. You can't go back and undo your mistakes. Believe me, I've thought about it. The order of events along any single path through space-time, what physicists call a world line, is fixed and agreed upon by everyone. What's relative is only the comparison of events at different locations, but it does mean that the grand cosmic now, the idea that there's a fact of the matter about what's happening simultaneously everywhere in the universe, that doesn't exist. That's a story we made up. And it turns out nature didn't read the same story. Now I'd like to bring in another piece of the puzzle, because we've been talking about relativity, which is the physics of the very large and the very fast. But there's another branch of physics, quantum mechanics, which deals with the very small, and it has its own strange things to say about time. In quantum mechanics, particles don't have definite properties until you measure them. An electron doesn't have a definite position, a definite momentum. It exists in a kind of smeared out state, what we call a superposition, until an interaction pins it down. When exactly that pinning down happens, and what it means, is one of the deepest and most contested questions in all of physics. But here's what's relevant to our discussion of now. In quantum mechanics, there's something called the uncertainty principle. My friend Heisenberg's great contribution, among other things. It says there's a fundamental uncertainty in the relationship between energy and time. You can't know both the energy of a system and the precise time of an event with arbitrary accuracy. The more precisely you pin down one, the less precisely you can know the other. Think of a photograph taken with a very fast shutter speed. You freeze motion beautifully. You can see every droplet of water, every eyelash in perfect detail. But that requires a very brief exposure, which means very little light, which means the image is dark and grainy. Now use a slow shutter speed, get all the light you want, and suddenly everything that was moving is blurred. You can't have both perfect sharpness and perfect brightness at the same time. Energy and time in quantum mechanics have the same kind of trade-off. Knowing one precisely necessarily blurs the other. What this implies, and I want to say this carefully, is that at the most fundamental level, even time itself is not perfectly sharp. The notion of now. This exact instant, this razor-thin edge, may not be meaningful down at the quantum scale. Time might be granular, pixelated in some sense, though we don't have a final theory that tells us exactly how. There's something called the Planck time, approximately 10 to the minus 43 seconds, which is the smallest unit of time that has any physical meaning within our current theories. Below that scale, our understanding breaks down entirely. We don't have a working theory of quantum gravity, and without it, we can't say with any confidence what time, or now, looks like at that resolution. What I find particularly fascinating is that both of our great physical theories, relativity and quantum mechanics, are telling us, from completely different directions, that now is not what common sense says it is. Relativity says there's no universal now across space. Quantum mechanics says now may not even be a perfectly sharp edge in time. Both of them are undermining the same intuition, the comfortable, obvious, natural feeling that now is real, universal, and precise. You know, when I was a young student, one of my professors told me that physics is the systematic destruction of common sense. I thought he was being dramatic. I've since concluded he was being modest. Now, here's something I always want to emphasize, because I think it's important not to let the strangeness become nihilism. Just because our intuition about now isn't exactly right doesn't mean it's useless. Newtonian mechanics isn't exactly right either. Einstein showed us that. But it's still correct enough to land a spacecraft on the moon. Our sense of now is a practical, workable, extraordinarily useful tool for navigating daily life. It just doesn't scale up to the whole universe, or down to the quantum world, in the way we assumed. The map is not the territory. Our mental picture of time, flowing, universal, sharp, is the map. The territory is richer, stranger, and more interesting. So let me take a breath here, and I'd invite you to do the same, and just sit with what we've covered. We started with a bird on a branch, and we've ended up with a universe in which now is a local, personal, motion, dependent, gravity, dependent, quantum, smeared concept that has no absolute meaning when you zoom out far enough. What does that actually mean for a human being going about their life? Well, practically speaking, almost nothing. You can still make your appointments. Your toast will still get cold while you're reading the paper. The ordinary rhythm of daily experience is built on a scale where all these relativistic and quantum effects are absolutely negligible. Your now and my now agree to an accuracy that makes the most precise atomic clocks look sloppy by comparison. But philosophically, and here I'm going to be a physicist doing philosophy, which you should always take with a grain of salt, it suggests something quite remarkable about consciousness and time. The vivid, immediate, undeniable feeling of now this sense you have right now that this moment is real and present. In a way that yesterday isn't that feeling is not a mirror of what physics tells us about the universe. It's something the nervous system constructs. It's a feature of minds, not of space-time. I'm not a neurologist, and I won't pretend to be one. But here's my layman's understanding. The brain receives signals from all over the body, from your eyes, your ears, your fingertips. Those signals travel at different speeds through different path lengths. By rights, They should all arrive at slightly different times. But you don't experience a jumbled, desynchronized mess of sensations. You experience a unified, coherent present moment. The brain does something quite clever. It waits. It holds back the faster signals until the slower ones arrive, and then it presents the whole bundle to your consciousness as a single synchronized now. You're always experiencing the recent past packaged and labeled as the present. The now you feel isn't the cutting edge of the universe. It's a brief report, edited and assembled by your own nervous system, delivered a fraction of a second after the fact. The conscious moment is, in a very real sense, a memory. I find this strangely liberating rather than troubling, because it means the feeling of being fully present, of existing right here and right now, is something you make, something your brain actively constructs from the raw material of sensation and memory. It's not handed to you by the universe. The universe doesn't have a now button, you do. And here's another thing. The fact that now isn't universal across space has an interesting personal implication. When you think about someone you love who's far away, when you think right now, wherever they are, they're doing something, that thought has a kind of warmth to it, a sense of connection across distance. And even though I've just spent considerable time telling you that right now, wherever they are, isn't a well-defined phrase at cosmological scales, it still captures something real at human scales. Because at the speeds we move and the distances we typically care about, relativity barely nudges the numbers. Your now and theirs are close enough to call the same. It's like the difference between a flat map and a globe. For driving across town, the flat map is fine. The curvature of the Earth doesn't matter. For flying around the world, it matters a lot. Physics gives us the globe. Life mostly lets us use the flat map. There's something in all of this that I find personally moving. I've spent a lot of time thinking about time, about what it is, where it comes from, whether it flows or just sits there. And I still don't have all the answers. Nobody does. But I think the uncertainty itself is interesting. The fact that we live and breathe and feel and love and grieve in this river of experience we call time. And yet time itself remains one of the deepest unsolved puzzles in physics. That strikes me as beautiful. We are creatures made of time, trying to understand time from inside time. That's quite a peculiar position to be in. Let me see if I can pull this together into something you can carry with you. First, everything you perceive is delayed. The light from your surroundings, the signals in your own nervous system. By the time you experience now, you're already experiencing a reconstructed past. Your now is assembled, edited, and slightly late. Second, the speed of light being finite and constant means that observers in different states of motion don't agree on which events are simultaneous. This is not a matter of confusion or measurement error. It's a genuine feature of how space-time is structured. Now is observer-dependent. Third, in the framework of general relativity, gravity affects the rate at which time passes. Clocks near massive objects run slower than clocks far away. The now experienced at different gravitational potentials is not the same. Fourth, the block universe interpretation of relativistic physics suggests that past, present, and future may all equally exist in a four-dimensional space-time, and that the feeling of time flowing is a feature of consciousness, not a fact about physics. Fifth, quantum mechanics introduces a fundamental blurring into the concept of when at the smallest scales, suggesting that even the sharpness of the present moment is not guaranteed by nature's deepest laws. And finally, and this is the one I want you to remember, none of this means that your experience of now is fake or meaningless or worthless. It means it's something more interesting than you might have thought. It's a construction, a practical, useful, beautiful construction, assembled by millions of years of evolution to help creatures like us navigate a world where the relativistic and quantum weirdness don't usually matter. But it's not a window onto some cosmic fact. It's a tool, a story we tell, a flashlight we carry into a universe that isn't itself organized around now at all. When you stand on the beach and look out at the ocean, you see the horizon, a clear, sharp line where the sea meets the sky. It feels real. It feels like it's there, at a definite distance, at a definite place. But of course, it isn't. The horizon isn't a thing. It's a perspective artifact. It exists only because of where you're standing and how far you can see. If you walk toward it, it moves. If you climb a hill, it recedes. It's a feature of your point of view, not of the ocean. Now is a lot like that. It feels like a real thing, a definite, fixed edge between what has been and what will be. But like the horizon, it shifts when you move. It depends on where you are in space-time, how you're moving, how strongly gravity is pulling on your clock. It is real. But real in the way horizon is real. Real as experience, not real as an absolute feature of the universe. I think that's a more honest and more interesting picture of time than the one we started with. And I genuinely hope, that the next time you catch yourself in a moment of pure presence, of feeling right here, right now, alive, you'll have just a little extra appreciation for what an extraordinary thing that is, not because the universe handed it to you, but because you, or rather your brain and your senses, and your billions of years of evolutionary history, built it from scratch, moment by moment, out of old light and nerve signals and memory. That's not less wonderful, that's more. Thanks for thinking about this with me. I'm always delighted when I get to spend time, whatever that is, on questions like this. See you next time.